we're back for the final installment of area of a plane region. Okay, if you notice the first one, we had two intervals in which we had to draw two rectangles, one for lower bound, one for upper bound. And when we did that, we had the upper bound area of 5, lower bound of 1. When we changed it to 4 rectangles, now we are getting a little bit closer to each other. As you know, the difference here is 2, the difference here was 4. So we're getting closer and closer to what the actual area is. And we kind of talked about that in the last video, that as this gets higher and higher, this end just keeps increasing more and more and more. Eventually you're going to get to that value that is exact for the area of the curve. Now, how does that look like mathematically? Well, let's explore that. All right, so the width of each of these rectangles, we're gonna, instead of calling it width, we're gonna call it delta x, because it's the change in x from here to here. So if you take this coordinate minus this coordinate, you'll always have the width. Same here. If you know this is 1.5 and this is 1, if you subtract it, you'll have the width of a half each time. So we're going to say it's delta x. Now this delta x was calculated by subtracting one endpoint from the other endpoint. So I'm going to do b minus a, because those are the x values for the endpoints, 2 and 0, so 2 minus 0. And I'm going to divide it by how many intervals or how many rectangles we want to draw, n. So the n is over here. That is how we figured out our delta x. If you know 2 minus 0 is 2, divided by 2 is 1. So that means our delta x was 1. If you remember from the video, the width of each of those first rectangles that we drew were 1. When we changed n to 4, now it was 2 divided by 4, which is a half. If you notice, the widths of all of these were a half. Okay, so that's how you figure out the width. For our length, all we did was take the function value at those certain x's for each one. So I'm just going to say there's some constant c at some ith term. So it says c sub I depending on which step we were at. So this first one was 1, and then the next one will be 2, 3, and 4 when the n was equal to 4. So this I number, this I value changed every single time you moved. If you notice, the delta x stayed the same each time because it was just based on the b and the a. This time, the length depended, or for the length, it depended on the function itself. So we have our length and we have our width. So this is going to be equal to our area. Our area is going to be equal to our length times our width. But again, we're trying to get this n value to go to infinity. So I'm going to set up a limit that goes from that n goes to infinity for, and we're going to do the limit of all the lengths and times all the widths and adding them together. So because I'm adding them together, I'm going to use that summation notation that we used before to go from 1 to n, and remember n's going to infinity, of this f of c sub I times our delta x. So if you look at it here, it's the sum of our length times our width, which is what we were doing before. We were adding the sum of that first rectangle plus the area of the first rectangle plus the area of the second rectangle plus the area of the other rectangles. So this time we're going to add all the rectangles going from 1 to infinity, because this time we're making infinitely many rectangles based on this limit. So the length times the width right here, this is our length, this is our width. Okay? So we're going to try to figure out right now what is the exact area under the curve using this notation. So here we go. So the first thing we're going to want to do is simplify. We can simplify this first one because we know it's 2 minus 0 over n, which is equal to 2 over n. So now we know our delta x. Right, so from here, I'm going to simplify and put things in, substitute things in just to make my life a little bit easier. So now, instead of delta x, I'm going to put in 2 over n. And what we can do for the f of c sub I, we can actually substitute in each value that we put in for the x based on what our delta x is. Because our delta x changed by 2 over n each time. So when it was 2 over 4, it changed by half each time. So since we're doing the index of 1 here, I'm just going to put 2I over n. So then it actually is going through each individual index for that summation. So now I still have the sum of the length times the width. Okay, let's simplify this a little bit more. So now f of 2I over n, I'm just going to plug that right into the function up there, and you end up with 2I over n squared times 2 over n. Now this is going to be equal to 4i squared divided by n squared times 2 over n. Now what we're going to do here is simplify this. You should get 8i squared over n cubed by multiplying across. Now what I'm going to do here is I can pull out the constants because the 8 is a constant and the n third to the third power is constant. So I'm going to pull that out in front and now of the sigma, so you should get the sigma of I squared. Now if you remember from the previous video, one of our summation properties breaks this I squared down, so you can actually simplify all of this right here to be equal to, this would be equal to n times n plus 1 times 2n plus 1 all over 6. Okay, from here I'm going to simplify. I can cross this out right here, so this would be to the second power. Okay, and then I can simplify this as well a little bit further. Here really quick, I'm going to simplify this. I'll cancel out that 4, I'll cancel out this 6. And then I'm going to simplify this numerator right here to be 2n squared plus 3n plus 1. Okay, now all of this is going to be divided by n squared, so you should end up getting the limit as n goes to infinity of, well, this right here would be 8n squared divided by n squared, which is 8, divided by 3, so I'm going to put 8/3 here, plus 3 times the 4 is 12n, right here, divided by n squared divided by 3, so that'll cancel right here to get 4n. And then last but not least, you'll end up with 4 divided by 3n squared. Now, since n is going to infinity, this goes to 0, this goes to 0, and you're left with 8/3 to be the area under the curve, which is actually the correct area under the curve of x squared. So that's how you use the limits in relation to the sigma notation to calculate the area under a curve of a function. So if you have any questions about this, let me know.